Hello everyone, my name is Mike Fang. Welcome to my TA application video. Today I'm going to pretend I am the TA for one of the course I'm taking this term, and then let's discuss the question 5 of homework 2. The question is like this: considering Dijkstra algorithm with a priority query for a variety of size n for a complete graph with edge weights randomly choosing between 0 and 1. The final question is, how does the number of decrease key operation actually scale with n? It's actually very easy to implement and do experiment to show the result, but to analysis how or why the result looks like some curve is hard. So let's start by a short review for the basic concept. Let's start with complete graph. So for a complete graph, assume we have n vertices, and then because all the vertices are connecting to each other, each vertices will have n-1 neighbors. So remember these attributes, and we're going to use it later. The second thing we need to review is the definition for decrease key operation. Let's consider a graph like this. We have roots nodes A, and then we have B and C. So let's run a Dijkstra algorithm on this graph. Let's expand it A first. So we have distance 3 and 1. And then in this case, the distance of B, the shortest path from A to B is 3. And here for C is 1. In this case, the second node we need to expand is C. And then we have here is 1. In this case, the distance for B will be updated to 2. In Dijkstra algorithm, each time of such an update will be called for a decrease key operation. So that's one thing. Okay, let's go back to the main problem. So how the number scale with n? Instead of considering the whole graph, we can start by one certain node. Consider here's the root node, here's the current node, and then one explored edges here will be corresponding to a path from a certain path from root to current node. Why? Because if this node has been expanded, then the root nodes, then the shortest path from root node to here is fixed. So each edges corresponding to one path, and we will have n-1 paths from roots to here. Because we are thinking about a general case, we assume we have no prior knowledge for how the weight is distributed. Actually, they are distributed uniformly. So the expectation for the size of all the edges are equal. That's the first equal. The second one is the expectation for the distance of all the paths from roots to a certain nodes are equal. That's the second equal. So go back to the question. Assume we have 3 paths here. Consider the third path. What is the probability of the third path can raise the decrease key operation? The answer is 1 over 3. Why? Because actually we are asking about the probability that the third path is the shortest path between 1 to 3 paths. In this case, you can notice that the probability that the first path raised an operation is 1, and then the probability of the second one is 1 over 2. So the whole numbers of decrease key operation can be triggered corresponding to current node. Will be everything. We can sum all the expectation together. So it's be 1 plus 2 plus 1 over 3. Let's go to next slide to write it. There'll be 1 plus, and then in the end, plus 2. How many paths we have? n-1. So it will be like this. This one can be approximated by this, right? And then this one is this part. It's n's harmonic number, Hn. And then Hn can be approximated by log n, because this is not mass class. So I'm just use the formula. And then basically log n is the expected number of decrease key operation based on one node. And think about how many nodes we have in the complete graph. We have n nodes here. So n log n is the total number of is expectation for total numbers of decrease key in a complete graph given n nodes. So are we prove the right things? Let's go back to the experimental result. So here, the diagram shows that our proof is right because as you can see here, the experimental result perfectly align with the curve for n log n. That's all I have for my TA application video. Thanks for watching.